Now, remember that this is a reference model. This is not a network protocol. So it doesn't make communications occur, but instead facilitates modular engineering and interoperability for standards with all of our different network components. Now, if you want to remember your layers, one of the easiest ways to do it from top down is to remember that all people seem to need data processing. This is one of the age-old mnemonics for going from top to bottom. If you're going from bottom to top, also you can write down, please do not throw sausage pizza away. What you'll notice is that with both of these phrases, the first letter of each word is the same as the first letter of the name of each layer. But probably the most important functional aspect of OSI in understanding our layered model is knowing that each individual layer is responsible for a specific set of tasks and operations. One of the benefits of the OSI model not listed here is its ability to improve our troubleshooting capabilities. This literally is one of the most functional aspects of having a layered model. If I can simplify or standardize or make my entire network look very modular, then doesn't it mean that I can actually break down each individual function to be able to troubleshoot it as such? That's exactly what this model does. But it only facilitates this type of troubleshooting if you understand what the layers do. So that's what we want to do at this point. Focus on each individual layer. Beginning with layer 1, which is the physical layer. The physical layer means binary transmission, which defines the electrical, mechanical, procedural, and functional specifications for activating, maintaining, and deactivating the physical link. Now that's the complex version. Think about it as whatever you can physically touch, the electricity, the actual positive and negative voltages that you're going to have on a wire that indicate a binary bit, whether it's on, a binary 1, or whether it's off, a binary 0. Remember that all the data communications are literally binary. It can be a positive or a negative voltage. The physical layer's job is to literally deal with these voltage changes when we maintain, activate, and deactivate the link, and be able to understand what information is being sent. Now, of course, there has got to be a layer that actually converts it into this type of a format. Because when the physical layer is sending bits, it's going to be responsible for clocking data, which means that it's going to always make sure that data is being clocked at the right speed. Obviously, the physical layer is always limited by the media that you have and by the digital encoding scheme that you're using. The physical layer's responsibility is clocking, but something has got to turn it into binary bits, and that's what the data link layer is for. The data link layer, sometimes called the framing layer, is responsible for taking upper layer data and actually converting it into frames, which of course allow it to access the media. This is formatting the transmission and allowing it to actually enter the physical layer. Now, of course, the official designation or definition of data link is it defines how data is formatted for transmission and how access to the network is controlled. In effect, what they're trying to say is, hey, I can do error detection. I can do flow control. I can understand exactly what has to take place between systems because you have got the data link layer and I have got the data link layer. And I am building frames and they're being sent as binary bits and you are receiving them and you are seeing frames and you understand, and yes, they are being received correctly because we can calculate that they are. That's what the data link's responsibility is. This is access to the media itself. A lot of the magic happens at layer 3, which is the network layer. This layer is responsible for delivering data packets that are actually routed between systems. It tells us what the ultimate destination of a data packet is going to be, whether it's going to go to another PCN, personal computer network system, that's on our network, or if it's going to go somewhere else, like out across the internet and will hit the router. Data delivery at the network layer involves routing of data packets, selecting the best possible path to deliver data, and providing any of the necessary addressing and path selections that are required for this process. Layer 3 is where you'll find routers. Routers are responsible for network layer 3. We also have layer 4, which is the transport layer, where end-to-end connectivity is handled. Now, here at the transport layer, we're going to see any transportation issues between hosts being mitigated. This layer allows a reliable data transport to occur from system to system. You want to think of the transport layer as more or less the last component which is used to actually provide reliable communications, because it ensures transport reliability. It also ensures that we have a virtual circuit that is maintained and terminated properly, and our fault detection and recovery information flow control processes are reliable. All these networking capabilities are being taken care of at layer 4, which is the session layer. This is typically done with sliding windows and ports. The session layer controls inter-host communication and establishes, manages, and terminates sessions between applications. The primary job of the session layer then is to make sure that we have a session properly established so that data can be sent properly from one system to another. Now, if this is a large data transfer, normally an initial session is set up, and that session is maintained and managed throughout the entire course of that conversation. Once that conversation is completed, the upper layer data is going to terminate the connection. The session layer will terminate the session, and the connection will reset. The session layer then is very, very important for many different applications. This is because most applications that run over our primary protocols are going to have some element of layer 5 built within them. They will also have an element of layer 6, the presentation layer, which is actually designed to represent data itself to the application. Now, the application resides above layer 7, which is called the application layer. But in fact, it is the presentation layer that will make any changes to the data itself, such as providing data formatting or data structuring, performing data conversion, or performing data encryption. Data that is coming in from the network is actually entering the physical layer and is coming up through the data link layer, then passing through the network layer, the transport layer, and the session layer. If the data must be changed at all, it's the presentation layer's job to actually present these changes to the application itself, and that's why it's named the presentation layer. Layer 7's job is to process data for the application. Now, the application, such as an email application or a database application in most cases, will exist just above layer 7. The application layer is typically responsible for resource control, for synchronization of peers that are specific to that application. It performs user authentication for synchronization or whatever is necessary for two applications to be able to communicate. So the application layer is very, very important to resource allocation for these applications. One of the most important things about utilizing the OSI model is an understanding that it does not actually make data communications occur, but provides the framework for vendors to be able to create applications and operating systems that can, in fact, make these communications occur. When you consider different applications, just think on these lines. There are actually only two different categories of user-based applications. One type is the standalone or local user-based applications. These are the applications that you would run only on your local machine. For instance, a word processing program is a good example. Then there are applications that are considered to be network applications. These can take advantage of the network. Even certain word processors can take advantage of the network, though, such as Microsoft Word. The idea is that an application can actually run locally above the application layer. It can continue doing so until it really must use the network. This means that an application can run locally until it begins to exhibit the traits of what the OSI model is trying to create. That is, an environment which is standard, that can utilize all the network protocols and components to be able to access the network. One of the most important aspects of networking is data encapsulation, where a user-based application actually begins to use the network. For example, here we have the sender of data. We're using a word processing application that is actually accessing a database server to grab some data from another location on the network. The sender of the request is going to have to now utilize the network stack or the network components on that computer to be able to access the physical media to get to the destination of this conversation on the network. What the sender will do is that he will actually take the original application data, which becomes user data, as you can see above the application layer. Now remember, whatever happens on and below the application layer is all based on function. That is, the function of the operating system that this computer is running, and the function of the network components that are actually running on this computer. For instance, the protocol or the network interface card that this computer is using. Nonetheless, the user data is actually passed down to some area in the operating system, which is going to provide access to the network components. Here, that user data is passed down to the function at layer 7. At layer 7, any information that is required for layer 7 to do its job, for example, to perform user-based authentication or possibly synchronization of peers, whatever is necessary, is added to the header to the original user data. This actually becomes data that will be passed down to the next layer in the network stack, which is the function of layer 6. Now at layer 6, a layer 6 header is added to the data. Now keep in mind that even if something does not need to change, we will always have this header being added to the existing data, and thus every single packet is going to look the same. In this case, let's say that there was some decoding that needed to take place between the user's application and the destination component, possibly a database server. So any information necessary in layer 6 to do the decoding would actually change in the header. This would then become data that will be passed down to layer 5, where my session can now be established with the target. Layer 5, or the session layer, will set up, maintain, and finally terminate my session once I'm through with my conversation. The layer 5 header is added, and this data is then passed down to layer 4, where typically some sort of port is utilized to access the target application or establish the connection between the two applications. The layer 4 header becomes data to pass down to layer 3, where routing and addressing occur. The layer 3 header will typically contain any information about the source and the destination addresses, and any routing information which is necessary to get this individual unit of data to its destination. This packet, the layer 3 information, gets added to the remainder of my data, and my data is finally passed down to the data link, or layer 2, where this data is going to be framed. Now, two very important things happen in layer 2 during this framing process. First, a layer 2 header is added to the existing information. The layer 2 header is going to contain a special set of addresses, which are known as MAC addresses. Both the source, which is the sender, and the destination, which will become the receiver in this particular conversation, are added to this layer 2 header. This is a way for the receiver to actually identify that this package is in fact destined for them. Also, at the end of this frame, we're going to have a typical component which is added. This component is known as a trailer. In this case, it is referred to as the frame check sequence, which is very accurate. This indicates nothing more than the mathematical computation of the information beginning with the layer 2 header all the way through the user data, which originated at the very top of my application. This mathematical computation allows an integrity check to be performed on the opposite end, once the frame itself is received for verification purposes. If the frame was received intact and without damage, then there was no corruption on any of the data bits. This is very important for ensuring the reliability of our networking from end to end. Note that framing will be very different for every protocol that we intend to use. Also keep in mind that framing will be slightly different for each network media type that we use. Once the framing process is complete, we will then convert the data into physical bits. The positive and negative charges of electricity, which are going to be sent across the physical wire. This is done by the physical layer, which will also provide any clocking of the line which is necessary to make sure that those bits themselves are sent at the proper speed, in the proper order, and can be properly received.